In this class, we discuss an important test or theorem of improper integration, which is known as Dirichelet theorem, or it is also known as Dirichelet test of convergence of the improper integral of product or product of function, right? And this test may be of two types. At first we discuss the type 1. In type 1 we take the integration whose range is infinity. That is, the range is infinity, so impropriety in the range, that is integration a to infinity fx gx dx. Okay, now see the statement of the first type Dirichelet test. Let fx be bounded and monotonic, may be monotonic increasing or may be monotonic decreasing in a to infinity, closed interval a to infinity, and fx tends to 0 as x tends to infinity, right? The function tends to 0 as x tends to infinity. Also integration a to t gx dx, where t be any value greater than a, okay, be integrable and bounded. That is, this integration is also bounded here, it is also given. Then we have to prove that, or then Dirichelet theorem says that integration a to infinity fx gx dx is convergent. This is the statement of the Dirichelet test of type 1, right? To prove this theorem, we use very important theorem here. Second mean value theorem of integral calculus. This is also very important theorem, and this is we know in two form. First form is Bonnet form and second form is Oyster's form. Here we use Oyster's form. And what is the Oyster's form of second mean value theorem? If gx be bounded and integrable in AB and fx be monotonic in AB, then there exists xi belongs to AB such that integration a to b fx gx dx, this is equal to f of a into a to xi gx dx plus f of b into xi to b gx dx. This is the statement of second mean value theorem of integral calculus in Oyster's form. And the second theorem we use here, this is also very important theorem, Cauchy's criterion of convergence, and this is given by integration a to infinity phi x dx is convergent is that for any given epsilon greater than 0 there exists m greater than 0 where m depend on epsilon, that is m, this is equal to m of epsilon, such that integration b1 to b2 phi x dx mod, this is less than epsilon for m less than b1 less than b2. This is the Cauchy's criterion of convergence. We state and prove this Cauchy's criterion in the previous class. We see in the link in the description box here. Okay. Now we go to the proof of the Dirichelet theorem. Here it is given that fx is bounded and monotonic. And from the condition of integrability, we know that every bounded monotonic function is integrable, right? So we say here fx is integrable. In a to t, where t greater equal to a, right? And then we use the second mean value theorem of integral calculus, because a to t gx dx is also integrable and bounded, it is given. So we get, or we use second mean value theorem, we get the result as integration t1 to t2 fx gx dx. This is equal to f of t1 into integration t1 to xi gx dx plus f of t2 into integration xi to t2 gx dx. Okay, this is the second mean value theorem, like this relation. Okay, here xi is lies between t1 and t2, and we can write a less equal to t1 less equal to xi less equal to t. Okay, now also it is given that integration a to t gx dx is bounded and integrable. Okay, so there exists capital A greater than 0 such that mod of integration a to t gx dx less than capital A for all t greater or equal to a. So we can write for this integration t1 to xi gx dx mod. This is given by integration a to xi gx dx this mod minus integration a to t1 gx dx, right? Because this is a, this is t1, this is xi, and this is t2. So we get here a to xi at first, and we subtract a to t1. So there remains integration t1 to xi. We need this integration, and we use the formula of modulus. This is mod of integration a to xi gx dx plus integration a to t1 gx dx, right? And this is less than a plus a, that is less than 2a, because integration a to t gx dx, this is less than a for all t greater than a. Here xi and t1 both are greater than a. Okay, we use this result here. We name this result as 1, this is as 2, and similarly we can write integration mod of integration xi to t2 gx dx. This is also less than 2a. Okay, and we name this is 3 and this is 4, right? Now we take this portion. It is given that fx tends to 0 as x tends to infinity. That is given that limit x tends to infinity fx, this is equal to 0. And what is the definition of this limit? Because the limiting value is 0 and x tends to infinity, so there for any eta greater than 0, there exists k greater than 0. This k is however large, such that mod of fx less than eta by 4a for all x greater than k or greater or equal to k. This is the definition of this limit. Okay, and we name this limit or this definition as number 4. Now from this definition we write two results. The first result is mod of f of t1, this is less than eta by 4a, and mod of f of t2 less than eta by 4a. Okay, and we name these two results as relation number 5. Now using relation number 5, relation number 3, relation number 4 and relation number 2, 5, 3 and 4 in 1 we get, and in relation number 5 we must write here T1, T2, these are greater equal to K, or yes, greater equal to K, because this relation hold only when x greater equal to K. Now from 1, that is from this relation, and using 3, 4 and 5 with T1, T2 greater equal to K, we get this is mod of integration T1 to T2 fx gx dx less equal to mod of f of T1 into mod of T1 to xi gx dx plus mod of f of T2 into mod of integration xi to T2 gx dx. Right? We put in this place from these two relation, this is eta by 4a and this is also eta by 4, right? And we write from 3 and 4, that is in the first integration we write here 2a and this is also 2a, and calculating we get this is eta by 2 plus eta by 2, that is less than eta. Okay, so we write integration T1 to T2 fx gx dx less than eta for all T1 or T2 greater than K or greater equal to K. Now we already say the Cauchy's criterion of convergence. What is Cauchy's criterion of convergence? A to infinity phi x dx is convergent. Here this term is total phi of x. Okay, fx into gx, this means phi of x. Is therefore is convergent is that for given epsilon greater than 0, this is epsilon, there is m means this is k, and m is only depend on epsilon, such that integration b1 to b2 phi x dx mod less than epsilon, that is integration t1 to t2 fx dx, this less than eta for all t1 t2 greater equal to k. So this integration is convergent, and we say that by using Cauchy's criterion of convergence, we say that integration a to infinity fx gx dx is convergent, and this is our required proof. We want to prove this result. Okay, and this is our required result. So we prove very easily this theorem, that is Dirichelet theorem or Dirichelet test of convergence of improper integration. But this is of first type. Here the range of integration is infinity, and we discuss in the second case where the range of integration is finite, but there be infinite discontinuity in the lower range, right? At first we see 2 or 3 important examples based on this theorem or applying this theorem. Here we take 3 examples to apply this theorem, and the first example is, this is very important example, this and this 3 example is very important. In the first example, we first split the integration as 0 to 1 sin x by x dx plus integration 1 to infinity sin x by x dx. Okay, now the first integration 0 to 1, this is proper integration, Why proper integration? Because we know that limit x tends to 0, sin x by x, this is equal to 1. So 0 is not a point of infinite discontinuity and 1 is obviously not a point of infinite discontinuity, so this is proper. Now we have to test only this integration. Okay, we here let fx, this is equal to 1 by x. Clearly this is monotonic decreasing, because if n increases then 1 by x decreases, and this is tends to 0 as x tends to infinity. Okay, so the first condition satisfied, and g of x, this is equal to sin x, and here integration 1 to t g of x dx, this is equal to 1 to t sin x dx, this is equal to minus cos t 1 to t, so this is cos 1 minus cos t. And if we take the modulus of this integration, and this is also mod, this is also mod, so this is less equal to cos 1 plus mod of cos t, and this is less equal to 1 plus 1, because the largest value of cos 1 or cos theta is 1, so this is less equal to 2. And we say that this a to t gh dx is integrable, because we integrate this term and this is bounded also. So using Dirichelet theorem or Dirichelet test, we say that integration 1 to infinity sin x by x dx is convergent. Okay, so we write here by using Dirichelet test, integration 1 to infinity sin x by x dx is convergent, and this is also convergent because the first integration is proper integration, and this is convergent to prove using Dirichelet theorem, so this integration is convergent. We prove the convergence of the first integration. Now we go to the second integration. The second example, we here also split the range of the interval or range of the integration as 0 to 1 sin x to the power n dx plus integration 1 to infinity sin x to the power n dx. Okay, now obviously this is the proper integration, because there is no infinite discontinuity in the range, or there is no infinite range, so this is proper and this is convergent. Now we test for this integration, and we write this integration 1 to infinity sin x to the power n dx as 1 to infinity, this is 1 by n into x to the power n minus 1 into n x to the power n minus 1 sin x to the power n dx. Okay, we write this integration as this type, and we let fx, this is equal to 1 by n into x to the power n minus 1. Obviously this is monotonic decreasing in 1 to infinity and tending to 0 as x tends to infinity. Okay, so the first condition of fx must be satisfied. Now for the second condition, that is integration 1 to t gx dx, and this is equal to 1 to t n x to the power n minus 1 into sin x to the power n dx, and if we put x to the power n, this is equal to z, then we get the integration as n x to the power n minus 1 dx, this is equal to dz, so we get the integration is sin z dz, that is cos x to the power n, this is the integration. and we putting this value, we get this integration is equal to cos 1 minus cos t to the power n. Now taking mod on both sides, we get integration 1 to t gx dx. This is less equal to mod cos 1 plus mod cos t to the power n, right? And this is less equal to 2, obviously. This is 1 plus 1, this is 2. And we say that the second condition, that is a to t gx dx, is integrable and bounded. So here also Dirichelet condition of convergence is satisfied by fx and gx both. So we say that the second integration is also convergent, and that is the integration 0 to infinity sin x to the power n dx must be convergent, right? This is the second example. And the last one is, it is very simple, and we take fx, this is equal to 1 by root x, okay? And this is obviously monotonic decreasing in a to infinity, and this is tends to 0 as x tends to infinity. So the first condition satisfied. Now here gx, this is equal to sin x, and integration a to t gx dx, this is equal to cos x minus cos x integration a to t, and this is equal to cos a minus cos t, okay? So we get mod of this, mod of this, mod of this, that is less equal to cos a plus mod sin a. Sorry, this is not cos, this is sin, this is also, sorry, yes, this is cos and this is cos. We are right here because the function is sin, so the integration is cos, okay? This is also cos, and we say that this is 1 plus 1, so this is equal to 2. So integration a to t gx dx is bounded and integrable. So by using Dirichelet test, similarly we say that the third integration is also convergent. So we apply this 3 example. In this 3 example, Dirichelet test of convergence. This is the end of this class. Thank you for watching.